Electromagnetic induction. In Form 2, we learned that a current carrying conductor has a magnetic field associated with it. The magnetic field exists in such a way that the direction of the field depends on the direction of the current through the conductor. To be specific, the direction of the field can be determined using various rules such as clock rule. For instance, when current flows upwards, the field exists in such a way that it is in anti-clockwise direction. The converse is true, that is, when now current flows downwards, the field is in clockwise direction. In electromagnetic induction, the reverse of what happens here is true. That is, a changing magnetic field induces current in a conductor. This phenomenon is what we call EM induction, electromagnetic induction, and this was discovered by Michael Faraday in 1831. This particular concept of electromagnetic induction is applied in large-scale production of electrical energy in power stations. In this topic, we are going to look at various concepts associated with electromagnetic induction as well as its applications. The induced EMF. Electromotive force is induced as a result of the phenomenon that we have stated above, the electromagnetic induction. So we say that EM induction is a phenomenon that results into an induced EMF. This particular process of inducing an electromotive force can be demonstrated in various ways. We'll start by looking at how an induced EMF can be shown in using a straight conductor. So we arrange the apparatus as shown, whereby we have two magnets, magnet 1 and magnet 2. We arrange them in such a way that we have the opposite poles facing one another, so that the field, magnetic field, moves from the north pole to south pole in such a manner. We then place a conductor which is connected to a galvanometer between the two magnets and observe what happens on the galvanometer. The observation made in this case is that when the conductor is moved, the pointer in the galvanometer also deflects. So we say that the pointer deflects when the conductor is moved. The conductor can be moved in two ways: vertically downwards and then followed by upwards. So the deflection of the pointer is only observed when the conductor is moved vertically downwards or upwards. This shows that current flows in the conductor when it is moved in such a manner. What happens then when the conductor is not moved? When the conductor is stationary between the poles, there is no deflection in the galvanometer. Meaning that there is no flow of current when there is no relative motion. So no induced current. What happens then when the conductor is moved parallel to the field? When the conductor is moved parallel to the field, no deflection is observed on the galvanometer. Meaning that the induced current is zero. Moving the conductor at an angle. When the conductor is moved at an angle, the induced current increases to a maximum when the angle is 90 degrees. From these observations, we can make a conclusion that current is induced when there is relative motion between a conductor and the magnetic field. The deflection in the galvanometer is always reversed when the direction of relative motion between the the conductor and the field is reversed. So, we therefore conclude that for current to be induced into the conductor, there must be a relative motion, which is also determined by the angle between the field and the conductor. Maximum current is induced when the angle is 90 degrees.